Let's visually analyze these copulas together using 4 density plots in the form of scatter plots. This will help illustrate how points are distributed in the U1, U2 space and what types of relationships between x1 and x2 can be modeled using different copulas. Chart A represents the Gaussian copula. Chart B shows the T-student copula. Chart C represents the Clayton copula. Chart D represents the Gumbel copula. Here, the term copula refers to a dot-based representation of the PDF. The more dots in a given region, the higher the PDF in that area. If we set the Gaussian copula parameter in chart A to a low negative value, we can see that dots align along a negatively sloped diagonal. The more negative the parameter, the tighter the dots concentrate around this diagonal. When we increase the parameter to a sufficiently high positive level, the situation reverses. Now, high-density regions appear in the tails of the distribution, particularly around the points 0, 0, and 1, 1. The dots now cluster around a positively sloped diagonal, running from 0, 0 to 1, 1. Now let's examine chart B, which shows the T-student copula. At the moment, rho is set to 0.1 and nu is 0.5. With these parameter values, we observe a natural tendency in the model where, in addition to the lower left and upper right corners, observations also cluster near the upper left corner, U1 close to 0, U2 close to 1, and the lower right corner, U1 close to 1, U2 close to 0. Relatively high density is noticeable in these corners. This confirms what we previously saw in the 3D density plot, where PDF peaks appeared in all 4 corners under certain parameter settings. The rho parameter of the T-student copula influences the PDF in a way similar to the Gaussian copula, meaning it sharpens the density concentration along the diagonals, particularly in the corners of the U1, U2 space. Let's verify this in one direction. If we leave nu unchanged but significantly increase rho, the density in the upper left and lower right corners strongly decreases, almost disappearing, as we can clearly see. At the same time, density in the lower and upper tails increases. A similar effect occurs along the entire diagonal from 0, 0 to 1, 1. If we increase nu to 100 while maintaining a strong positive correlation, the overall density decreases. The dots that were previously aligned along the positively sloped diagonal begin to scatter. Now, let's turn to chart C, which represents the Clayton copula. We already know that theta is greater than 0 and controls how tightly the dots cluster, particularly in the lower tails. For example, if we set theta to a relatively high value, such as 11, we can see a very strong density concentration along the positively sloped diagonal. The strongest density appears around the point 0, 0. As we move up the diagonal from 0, 0 toward 1, 1, the density gradually decreases, but it remains higher than it was for lower values of theta. The Clayton copula is well suited for modeling positive dependencies, especially those that are particularly strong in the lower tails. Finally, let's look at the Gumbel copula in chart D. The Gumbel copula models positive dependencies, particularly strong dependencies in the upper tails, where U1 and U2 are close to 1. This corresponds to cases where x1 and x2 take high values in their respective domains. If we significantly increase theta, setting it, for example, to 12, we see that in the upper right corner, the dot density is the highest. However, the density remains relatively high throughout the entire plot. The dots strongly adhere to the positively sloped diagonal, running from 0, 0 to 1, 1, even in the middle section of the plot. That concludes the basic introduction to copulas. This should be fully useful at this stage of the course when we begin discussing Copula generation using 3 selected methods.